Okay, so this is lecture 13, properties of Laplace transforms, and we'll see what happens when you multiply a function by t, multiply by an exponential, and Laplace transforms with derivatives. So suppose we have a function and we multiply by t, and we want to know what is its Laplace transform. So a little notation first. The Laplace transform of f of t is also called capital F of s, and it's defined as this particular integral. So that's what Laplace transform of f of t is. So what is f prime of s? What's the derivative of the Laplace transform? Well, that's the derivative with respect to s of this integral. And generally, the fundamental rule of calculus tells us that we can interchange differentiation and integration as long as we're not tinkering with the variable that is being integrated. So since we're differentiating with respect to s and integrating with respect to t, we can move the differentiation inside of the integral. So back up here, f prime of s is the integral from 0 to infinity of d by ds f of t. The only s we have is here, so we're just going to treat t as a constant when we do the differentiation with respect to s. We get minus s e to the minus st f of t dt. But we're integrating with respect to t, not with respect to s. So we can pull that s outside. So we're differentiating with respect to s. So the derivative of e to the minus st is going to be minus t e to the minus st f of t dt, because the derivative with respect to s, you pull down the t as if it was a constant. So this becomes minus the integral from 0 to infinity of e to the minus st t f of t dt. But what the integral is then is e to the minus st times this function here. So f prime of s is actually minus equals minus the Laplace transform of t f of t t. Oops, t. So Laplace transform of t times a function is minus, there's the minus sign, the derivative of the Laplace transform. And so we can continue this, right? The Laplace transform of t squared f of t is equal to minus the derivative of the Laplace transform of t f of t, because that's what multiplying by a t does, up here. But the Laplace transform of t f of t is f prime of s, minus sign, and so the minus signs cancel out, and we just get the second derivative of s. Oops. So what's the Laplace transform of t cubed f of t? Well, this is the Laplace transform of t times t squared f of t. So that's going to be minus d by ds of the Laplace transform of t squared f of t. But we just calculated that the Laplace transform of t squared f of t is the second derivative. So it's minus f third derivative. So t cubed means third derivative. So t to the n times f of t, you get a -1 to the n because the sign changes every time, and then you get nth derivative. So what's the Laplace transform of e of just 1? So the Laplace transform of 1 is integral from 0 to infinity e to the minus st, 1 times that dt. And we do a substitution, u equals minus st, du equals minus s dt. And so this becomes the integral from 0 to infinity of -1 over s e to the u du. Oh, leave this as a plus, actually. So this will be a plus, this will be a minus u. And then this is 1 over s e to the u minus e to the u evaluated from 0 to infinity, e to the minus u. And that's 1 over s. The limit is e to the minus u goes to infinity is 0, minus 1. So if we got a minus sign, it should be minus e to the minus u. So then this minus sign, which comes from the integration, can come out there, and we get that, and we get 1 over s. So Laplace transform of 1 is 1 over s. What's the Laplace transform of t? Laplace transform of t is, well, that's the Laplace transform of t times 1, and we know what multiplication by t does. That means we want minus d by ds of the Laplace transform of 1. Minus d by ds of 1 over s, because that's that derivative. But the derivative of 1 over s is minus 1 over s squared, and a minus times minus is a plus. So what's the Laplace transform of t squared going to be? Well, it's the Laplace transform of t times t. So it's going to be minus the derivative of the Laplace transform of t. But we just calculated that. That means it's going to be minus the derivative of 1 over s squared. And the derivative of 1 over s squared is minus 2 over s cubed. So we get a 2 over s cubed. And the Laplace transform of t cubed is Laplace transform of t times t squared equals minus d by ds of the Laplace transform of t squared equals minus the derivative with respect to s of 2 over s cubed. Now, when we differentiate s to the minus 3, which is what we have here, we pull down another 3, and it's a minus 3, so the minuses cancel out, and we get 2 times 3 over s to the 4th. And then you can guess whether it's going to go. The Laplace transform of t to the 4th is going to be 2 times 3 times 4 over s to the 5th. The Laplace transform of t to the 5th will be 2 times 3 times 4 times 5 over s to the 6th, etc. Keep in mind that we have a special notation for this. 4, by the way. N factorial equals 1 times 2 times 3 times 4 times 5. So Laplace transform of t to the 5th is 5 factorial over s to the 6th. This is called n factorial And so in general, what are we getting for the Laplace transform of powers of t is n factorial over s to the n plus 1. So Laplace transform of a polynomial, we've been meaning to get to this. Laplace transform of t squared plus 3t plus 5 is the Laplace transform of t squared plus 3 times the Laplace transform of t plus the Laplace transform of 5. Right, and this is using the linearity of the Laplace transform. We can find the Laplace transform of each term separately, and the constants can come out of the Laplace transform. So this is 2 over s cubed plus 3 times 1 over s squared plus 5 times 1 over s. 1 over s. So there's a Laplace transform of that. Just take the Laplace transform of each term and add them together. So what's the Laplace transform of t cosine bt and t sine bt? We see these sometimes in when we're doing resonance. We came up with these as solutions to differential equations. So the Laplace transform of t cosine bt is minus the derivative, because that's what multiplying by t inside the Laplace transform of the Laplace transform of cosine bt. And that's equal to the Laplace transform of cosine is s over s squared plus b squared. So we have to use a quotient rule here. The derivative is going to be the minus, that's the minus sign out front, times s squared plus b squared, which is the bottom, times the derivative of the top, which is 1, minus the top times the derivative of the bottom, which is 2s, all over s squared plus b squared, quantity squared. And tidying all that up gives us the Laplace transform of t cosine bt equals s squared minus b squared over s squared plus b squared, quantity squared, right? So 2s squared here, s squared minus 2s squared, so we end up with a b squared minus s squared in the top, but there's a minus sign outside. Laplace transform of t sine bt goes the same way. Minus d by ds is a little bit simpler of the Laplace transform of sine of bt, which is minus d by ds of b over s squared plus b squared. So there's no s in the top here for sine, and so we just end up with 2bs over s squared plus b squared, quantity squared in the bottom. So there is our Laplace transforms of t cosine bt and t sine bt. And again, we want to be able to find Laplace transforms of things involved with differential equations. These are all functions that show up in solutions to differential equations. We also get multiplications by exponentials. So we want to show that this relationship is true because we need to find Laplace transforms of things like this. So if f of s equals L, if f of s is the Laplace transform of f of t, which is defined as e to the minus st, f of t dt, well, we can always replace the s by s minus a. but we have to replace it in both places, in the integral and in the Laplace transform. And so this becomes the integral from 0 to infinity of e to the minus st, right? That's here, and then e to the at. So I've got a minus a, which is a plus a t f of t dt. But what is this? If we consider this as a function, this is just the Laplace transform of whatever that is. And so that gives us that formula. So that's nice. An exponential gives us a shift in the s plane. So multiplying by an exponential with a variable t means that the Laplace transform over an s has a shift. So we know the Laplace transform of cosine bt is s over s squared plus b squared. The Laplace transform of e to the at cosine bt, which we saw a lot in solving homogeneous second order differential equations. All that does, the multiplication by the e to the at is to shift the s's to s minus a's. And same thing for, oh, there should be sine here. The Laplace transform of sine of bt is b over s squared plus b squared. So the Laplace transform of e to the at sine of bt is b over s minus a quantity squared plus b squared. So that's where those came from. Now, here's where we get to the point where we can actually start thinking about solving differential equations, right? What's the Laplace transform of derivative? And there's a very nice formula for that, which is this. So the Laplace transform of a derivative is integral from 0 to infinity e to the minus st f prime of t dt. And this is set up for an integration by parts. So we'll take u to be e to the minus st. We'll differentiate that with respect to t, and that gives me minus s e to the minus st dt. And we'll take dv to be f prime of t dt. When we integrate that, we just get f of t, because the integral of a derivative is the function itself. So using that, we get u times v, which is e to the minus st times f of t. Remember, it's a definite integral from 0 to infinity. And then we get minus the integral of v du. So integral from 0 to infinity of v, which is f of t, times minus s e to the minus st. So the minus will come up front, this minus and the minus, this minus here and the du, and the minus from the integration by parts formula combined to give me a plus f of t s e to the minus st dt. So to finish this off, we need to know what this first thing is, e to the minus f of t so this term, what does that turn out to be? Well, we deal with this by saying we want, anytime we have something going to infinity, we need to limit as b goes to infinity of e to the minus sb f of b minus e to the minus s times 0 times f at 0. Because we plug in the infinity, right, that gives us this term, minus what we get when we plug in the lower limit, which is this 0. Okay, so here we're going to assume s is greater than 0, so that this is, the exponent is negative. And we're also going to assume that f behaves in a way so that this limit actually goes to 0. this is a b here. So we want e to the minus sb times f of b to actually go to 0. And that puts some limits on what functions can have Laplace transforms. That is an interesting thing in math to study that. But all our functions are nicely behaved, so we can just assume that these limits exist and go to 0. So this becomes 0 minus f of 0, because this is just 1. Great. So all of this then becomes minus f of 0 plus s integral from 0 to infinity, f of t e to the minus st dt. And all of that then becomes s times the Laplace transform of f. Right? That's what this integral is, minus f of 0. So the Laplace transform of the derivative, that's this guy, is s times the Laplace transform of the function, that's this guy, minus the value of the function at 0. Great. So what's the Laplace transform of the second derivative? Laplace transform of the second derivative is the Laplace transform. Well, you have to remember that the second derivative is the derivative of the first derivative. And we just figured out a formula for Laplace transforms of a derivative. So this is going to be s times the Laplace transform of f prime of t minus f prime of 0. Just taking this formula here and replacing the f prime by an f double prime and the f by an f prime. Well, we know what the Laplace transform of that is because we just calculated that. That's s times s Laplace transform of f of t minus f of 0, and then minus this f prime of 0 that's here. So Laplace transform of the second derivative is s squared, because we have to distribute this s here, minus f of 0 minus f prime at 0. Great. So what's the Laplace transform of the third derivative? Well, that's going to be s times the Laplace transform of the second derivative minus the second derivative at 0. So it's just taking the formula for the first derivative and saying, well, the third derivative is the derivative of the second derivative. We know what taking the Laplace transform of a derivative is. It's s times the Laplace transform of the function minus the function at 0. So, but we know what the Laplace transform of f double prime is. It's s squared minus, s squared times the Laplace transform of f. I just totally forgot to put that in there. Minus s f at 0 minus f prime at 0. S squared minus s squared times the Laplace transform of f minus s f 0 minus f prime of 0 minus f double prime of 0. So the Laplace transform of the second derivative is all this. Multiply through by the s, you get s cubed. Laplace transform of f minus s squared f at 0 minus s f prime at 0 minus f double prime at 0. So we can keep going on and on and on. If f of s is the Laplace transform of t, and f, if we have f with a little parentheses around a k as the exponent, that's usually the kth derivative of f. So what are we getting? The third The Laplace transform of the third derivative is s cubed times the Laplace transform of f minus s squared f of 0 minus s f prime of 0 minus f double prime of 0. So if we continue the pattern, the Laplace transform of the fourth derivative of t should be s to the 4 Laplace transform of f minus, and then we just multiply each of these terms here by s cubed f of 0 minus s squared f prime at 0 minus s f double prime of 0 minus the third derivative at 0. Right? And then the Laplace transform of the fifth derivative will be s times the Laplace transform of the fourth derivative minus Laplace transform of the fourth derivative minus the fourth derivative at 0. But the Laplace transform of the fourth derivative is this whole thing. So what does that mean? If I distribute the s across this whole mess, I'll get an s to the fifth, and then an s to the fourth here, an s squared cubed there, an s squared, and an s, and then minus that. So s to the n minus times the Laplace transform of f of the function, and then a decreasing powers of s times derivatives of various values. And so that gives us the derivative. So that's the derivation of all the formulas that we're actually interested in. Here's the giant list of transforms of roles. Here's a function. Here's its Laplace transform, e to the at, sine bt, cosine bt, 1 t to the n, e to the at, sine bt, e to the at, cosine bt, t sine bt, t cosine bt. This is pretty much most all of the functions that we have seen, except for functions of the form t e to the at, t squared e to the at, etc., which you can figure out on your own if you need to. And then there are certain rules about Laplace transforms. This is the definition. We have an inverse transform, which means if you know the transform, can you figure out the function? Linearity, k1 f of t plus k2 g of t becomes k1 times the Laplace transform of f plus k2 times the Laplace transform of g. Here's the big formula for derivatives. This is the formula for first derivatives. This is the formula for second derivatives. Multiplication by t just means take the derivative of the function, right? So multiplication by t to the n is nth derivative, but t f of t, its derivative, its Laplace transform is minus f prime of s, and the multiplication by e to the at means shift the Laplace transform from f of s to f of s minus a.